All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today?
Pretty good.
Good to hear. All right, it's the last lecture before the midterm. I know there's a little bit of uneasiness in the air as there always is, but so today we are starting something new. So today kind of marks the official start to kind of the second half of the class, which is I would say kind of more general finite elements. So far, we've used finite elements in what we call the direct stiffness method. That's a very specific application of it, and kind of the whole purpose of direct stiffness was just to illustrate to us um, just the whole process of what it takes to run an FEA. But it's not really modern. It's not the modern approach that people take. So today, we're going to start our discussion of modern FEA. We're not going to get, it's going to take us a while to get there, just because there's a lot of mathematical preliminaries to get there. But today we start. Okay. And just know that what we cover in class today is not going to be on the midterm. So I've already written the midterm. It's based on what we've covered so far. A couple of the problems took a long time, so I ended up cutting one of the problems. So originally there's going to be three direct stiffness problems. Now it's only two, and so because they did take a while for me to do so. So hopefully that alleviates some stress a little bit on. Okay. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. Okay. So the subject for today, actually, again, actually has nothing to do with finite elements. We're going to go over the strong and what's called the strong and weak forms of boundary value problems. Okay. All right. So, just like I just mentioned, finite elements is more than just solving, trusses and springs and beams, right? In general, finite elements gives us a way to solve differential equations on a computer. Okay, so at its core, FEA is a way right? So this is kind of how FEA started. So FEA started as kind of an alternative way to solve differential equations. Right? Actually, interestingly, if you look at the history of development of FEA, it actually didn't even have anything to do with computers. Although nowadays we associate FEA with computers, they're kind of synonymous with each other. FEA was just kind of a way just to kind of formulate differential equations in a different way and solve for its solution. And it didn't really gain enough traction until computing kind of really became a thing. Okay. But that's what FEA was designed to do. It was to take differential equations and solve for its solution using an algebraic method versus a differential equations method. Okay. Okay. And so that means, for every finite element problem that you do, and this includes our direct stiffness methods as well, there is an underlying what we call boundary value problem. And so if you've never heard the term boundary value problem, essentially a boundary value problem has three components. Okay. Okay. So the first component of a boundary value problem is the governing differential equation. So there has to be some kind of differential equation that we have to solve in our boundary value problem. Okay. Number two, there has to be some kind of defined geometry or defined domain. Okay. So the definition of where we're solving our equation must be clearly defined. And number three is boundary conditions. And so boundary conditions, we've talked extensively on at this point in the class. So boundary conditions basically tell you the behavior of your solution or any kind of external effects that are going to affect your solution at the extremities of your domain. Okay. Okay, so every FEA problem starts with a boundary value problem, and FEA basically just provides us a method or a way to solve this boundary value problem. Okay. Okay. So at its core, FEA is a method for solving these kinds of problems here. Okay. And so what we're going to start here, for the second half of class is, we're going to go through how FEA solves a general boundary value problem. Okay. One which has a differential equation, one that has, an arbitrary domain, one that has boundary conditions. Okay. Because so far, we've only looked at very specific situations that have to do with springs and beams and trusses and frames. Okay. Okay. So to start our discussion, we have to talk about, the so-called strong forms and weak forms of a boundary value problem. Because for any boundary value problem, there are multiple different ways that we can express it mathematically. Okay. Okay. And despite its names, right? And so, the naming is kind of unfortunate because, I think people associate strong with good and weak with bad. The strong form and weak form, it doesn't imply that one form is better than the other, right? They're simply just different ways to formulate the same problem. Okay. Right. So I kind of have to emphasize that every year or every time I teach this, even though we're calling one the strong form, one the weak form, the strong or weak does not imply just general strength or general weakness. It's more just how the equations are applied. I think it'll make sense kind of soon. Okay. And in fact, the strong form is probably what you're most familiar with when you've seen boundary value problems in the past, when you've seen them in like a math class or maybe another engineering class. Typically it's expressed in the strong form. Right, that's kind of the traditional way to kind of express a boundary value problem. Okay, the weak form is going to be useful for us because actually the finite element formulation for any given boundary value problem is based on the weak form. Okay? And what you'll see later today is that the weak form actually has some very useful properties that you don't see in the strong form that actually make it very conducive to doing the finite elements. Okay, so for this whole entire lecture today, and this lecture will of course bleed into next Thursday as well after the midterm. We're actually not going to touch finite elements, and so we're going to be kind of taking a break and just kind of doing math for a couple lectures. But this is kind of important preliminary stuff in order to get into general finite elements. Okay. Any questions on this so far? Okay, so to kind of help facilitate our discussion here, we're not going to go just purely from a math perspective, just because this is an engineering class. And so we're going to look at the strong and weak forms through the lens of some very common problems that we see in engineering. One of them being elasticity, and the other being heat transfer. Okay, so let's look at the 1D elasticity equation in the strong form. Okay. All right, so for elasticity, we're essentially solving a structural mechanics problem. So not all that different than what we were solving for in direct stiffness, okay? So let me go ahead and draw the geometry here, okay? So let's say that we have a particular structure that looks like this, okay? Maybe this is some kind of truss element, right? And let's say that, I kind of drew it a little bit too far to the left, unfortunately. Let's say that we're going to be applying some kind of compressive force, okay? So we'll call that T bar, right? So that's going to be some applied compressive force at the end of the truss, okay? All right. And what we're interested in, right? So let's say we're interested in after we apply that that force there, right? We want to see how much this this bar is going to displace. Okay, so we're going to solve for u as a function of x, where u here is the deformation of the bar as a function of x. Okay. Okay. Okay, so on the surface, this looks similar to, what we've been doing for trusses and beams, right? But, there is one distinction here, right? So if you think about, the way we solve our direct stiffness problems, we only were interested in the solutions at particular locations in our geometry, right? So we only could solve for the solution at the nodes, right? We're not doing that here. So we're actually solving for the deformation at all points in X, right? So this is a continuous function, not a discrete problem yet. Okay. I apologize. My iPad or my iPencil is kind of acting up a bit today. Okay. All right. So how are we going to do this? And I forgot one thing. So let's also assume that we have something called a body force that's being applied onto our structure here. Okay. So these purple arrows here, this will be some function b of x, which we'll call the body force. Okay. So the body force is some kind of force that's distributed throughout the entirety of the structure. Okay, so it's some kind of internal force. You can think of it like that. Okay, so some common examples of body forces that we see in reality are gravity, right? So when gravity applies force on an object, it kind of applies it throughout your entire body because you're sitting in a gravity field. Okay. Another example could be maybe you have like an electromagnetic field, right? So you have some kind of electromagnetic field that's kind of pulling you in a certain direction. Okay. So the body force, is something that we just include just for completeness in our equation. There are a lot of situations where we don't include the body force, but let's include it in our calculations here. Okay. Okay. We also need to know the properties of the bar as well, and we'll keep these as general as possible. Okay, so first of all, we have the Young's modulus of the bar. Okay, so E of x here, this is the Young's modulus. Okay, and we are assuming that it can actually change with distance here, so it is a function of x. And we also have A of x, which is the cross-sectional area. All right, and so that can also change with x. Okay. All right, and the last thing that we need here is we need the overall length of the bar. So we'll say the bar here has a length of L. All right, so what we want to do, first thing is that we want to derive the governing differential equation for this particular situation. Okay. Because if we're looking at this in terms of a boundary value problem, we already have 2 out of 3 of the ingredients, right? So first of all, we already have our geometry, right? So our geometry or domain in this case is going to be the bar, right? And we have our boundary conditions. And so we know that on the left-hand side of this bar, we have some kind of applied compressive force. And on the right-hand side, we have a fixed support. So we know exactly all the external effects. So the only thing we need to complete our boundary value problem is our governing differential equation, okay? Now, for this particular case, I'm going to go through the derivation just to kind of show you this is not something that you need to do on a regular basis. But, just because it's, just because it's our first time, I do want to go through the derivation just to kind of show you what it's like. Okay. Okay. All right. Any questions on any of this so far? Okay. All right, so let's go ahead and go through the derivation. So what I'm going to do, or the way we're going to start this, is we're going to cut out a sliver of this bar, and then we are going to perform a force balance. Okay. All right, so let's say we're just going to cut out I've used red before, use green. Okay. So let's say we're going to cut out a small slice of the bar just like that. Okay. Okay. So we cut that piece out there. We have this piece of the bar just like that. Okay. All right. So let's go ahead and quantify all the different forces that we experience on this thing. Okay. Because one thing that we know, right, or one thing that's kind of implied by our situation here is that this entire bar is in static equilibrium, right? So it's not moving. Okay. Right. And so if the entire bar is in static equilibrium, that means each individual slice of the bar is also going to be in static equilibrium. Okay, so that means if it's a static equilibrium, if we add up all the forces that are being applied on the bar, then they all have to add up to 0. Okay, okay, so let's quantify the forces that are being applied on this slice here. Okay. Okay, so on the one hand, in this slice right here, we do have our contribution from the body force. Okay. Right, so this right here is B. And we'll say that this slice is appearing at some location X, okay? Where the width of this slice, we'll say the width of this slice is dx right here, right? And so if we evaluate the body force right in the middle of that slice, then the body force is going to be applied at B of x plus dx plus divided by 2. Okay? So essentially, we're evaluating our body force at just a single point right in the middle of our slice, okay? Okay. Another thing that we have here is that after we apply a force, we just know from just the theory of elasticity that internal forces are going to be developing within the bar. Okay. All right. So we're going to have one internal force that is going to be applied this way. Okay. So we'll call that n of x. And we have another internal force that's being applied on the other direction. So this is n of x plus dx. Okay. For n of x here, this is an internal force that develops due to the elasticity of the bar. Okay. Right. So you take any elastic structure, you apply a force. These internal forces are what's developed. Okay. Think back to our first ANSYS activity, right? So in that ANSYS activity 1, we had our plate with a hole. We applied a force, and that created a stress distribution within the plate. Okay. So this is essentially that same thing as that stress, right? So whenever you have any kind of structure that's under some forces, there has to be some internal forces or internal stresses that develop. Okay. And the main purpose of these internal stresses is so that every location or every part of that structure remain in static equilibrium. Okay. Okay. But that normal force is going to be, or excuse me, that internal force is going to vary from point to point, right? So that's why we evaluate n at some function x, and we evaluate at n of x plus dx. Okay. Okay. All right. So let's go ahead and sum the forces. Okay, so we only have one dimension of forces here, which is in the x direction. So we sum up the forces in the x direction. Okay. All right, so we're basically just going to add up all the forces together here. So this is going to be a minus nx, right? Because that nx is pointing to the left, plus n of x plus dx, okay? Because that force is pointing to the right. Okay. We also need to add our body force here. Right, because that body force is going to the right. But in order to make sure that the units match up, we're going to take this body force and we're going to multiply it by dx as well. Okay. All right, so the reason we did this, and I apologize, I should have mentioned this while we were going over the problem, is that body force, usually the definition of body force is that it's defined in terms of a force per length. Right? And so in order to make it the same dimensions as the internal force, we have to multiply by dx. Okay, so we have a very simple equation here, right? You might already kind of predict what we're going to do, but essentially, we're going to make a differential equation for this. Okay. So first thing we're going to do is we're going to divide this entire equation by dx. Okay. And then what I'm going to do is I'm going to swap just the order of these first two terms here. So we're going to have nx plus dx minus nx, all divided by dx, plus b of x plus dx divided by 2, all equals to 0. All right. So hopefully that first term there, that fraction there looks familiar to you. That is the exact definition of a derivative, right? But of course, in order to turn this into a derivative, we need to take the limit as dx goes to 0, okay? So we've already considered a small slice here, but that dx is still something finite. And so in order to actually get a derivative from this, we need to take the limit as dx approaches 0, right? And that gives us the exact definition of our derivative here. So that's going to be dn dx plus b of x, right? We took the limit as dx goes to 0, and so that means that dx over 2 term there is also going to go away. Okay? And all of that is equal to 0. Okay. All right, so what we have here, just through that very kind of simple derivation, just by looking at the force balance, is we have a differential equation that governs the evolution of the norm of the internal force within the bar. Okay. Okay. Good. Any questions on this so far? Kind of what we've accomplished here in the proof so far. Okay. Good. All right. So this equation is valid. It's good. But it's not the most useful for us, right? Because if you look back at our original problem statement, okay, right, what we want from this problem is not the internal force, but we want the deformation of our rod as a function of x. Okay. Now, our equation here doesn't have deformation, it has normal force. And so we need to kind of work on this equation a little bit more until we can get that normal force, or excuse that deformation. Okay. So to do that, we need to make use of some definitions here. Okay. Okay, so first one that we will plug in is we can say that the internal force at any given point within the rod is equal to the product of the area, where this area here is the cross-sectional area, okay, which we know is a function of x, right? So that was one of our definitions, that we know the cross-sectional area as a function of x, okay, multiplied by the internal stress at that location. Okay. So that's just kind of the definition of stress, right? So stress is just a force over an area. You can kind of manipulate that and multiply both sides by area, and we get that normal force is equal to area multiplied by stress. Okay. Now, why is this useful, right? Kind of seems like we're going backwards here, but this stress here we can actually put in terms of strain, right? Because we know from Hooke's law, the other Hooke's law, not the Hooke's law involving springs, this is the more general Hooke's law, is that the stress in any kind of structure, if you assume linear elasticity, is equal to the product of the Young's modulus. Okay. So E of x here, this is the Young's modulus. Okay. And we're being completely general here, so we're assuming that the Young's modulus can actually change in space. Okay. Which is quite unusual, but it can happen for certain composite materials. Okay. And then this epsilon here, this is the strain as a function of x, right? So stress is equal to Young's modulus times strain. So that's the central formula for linear elasticity. Okay. Now, this is helpful because the strain we can put in terms of the deformation, okay? Because strain is nothing more than just du dx. Okay. So strain is just a measure of how the deformation of the rod is changing as a function of x. Okay. So you kind of, it's kind of a chain here. So if you plug in du dx in for strain, we plug in, E times strain in for sigma there, and we plug in A times sigma in for n. So it's kind of a long chain of reactions here. But essentially what we get is n of x, right? So we perform all of those plugging ins is equal to area multiplied by the Young's modulus. Okay, so A of x multiplied by E of x multiplied by du dx. Okay. And then what we can do from there is we can plug this back into our differential equation, right? Because now we have an expression here for the internal force as a function of the deformation. Now the deformation does appear as a derivative, but that's okay. Okay. So we go ahead and plug that back in, and we get our governing equation for linear elasticity in the one-dimensional case. Okay. So you have d dx of E of x, A of x, times du dx plus v of x is equal to 0. Okay. So this right here is our 1D elasticity governing equation. All right. Any questions on how we got that? How we got that result there? Okay, good. All right, so we now have a differential equation, right? It's there's a lot going on there, but we have one in terms of the deformation. So that satisfies that property there. Okay. Last thing we'll do before we actually try to solve this is let's go ahead and take our boundary conditions and put it in a mathematical form that we can use. Okay. 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 So first one that we have here is we have the compressive force on the left-hand side. And in fact, actually, so that compressive force is actually compressive stress. Okay, so this is a compressive okay. So this is a compressive stress on the left-hand side. Okay. Okay. So let's go ahead and draw our free body diagram for this as well. So let's perform a force balance. Okay. All right. So we have our block here. Once again, we're going to take just a small sliver. So our small sliver here has a width of dx. Okay. And so on one side, we are going to have our compressive traction or compressive stress. Okay. Right. So this is our T bar here. Okay. In the middle of this, we also have our body force, and so we can't forget that. So we have our body force here. So this is our B of x plus dx divided by 2. Or x here. So I apologize. So we're accounting for this at the left-hand side of the domain, right? So that means our x value here is equal to 0. Okay. So instead of b of x, we're going to say this is going to be b of 0 plus dx over 2. Okay. Remember, this is a boundary condition, so we can state that we're at a very specific location of x in our domain. Okay. All right, and then of course we also have our internal force. So our internal force is going to be n of, well, technically it's n of dx. Because that's the internal force that's on the right-hand side of this little sliver here. Okay, and then that's what's going to be balancing kind of everything out here. Okay. All right, so let's go ahead and take a force balance here. Okay, so we're going to take some of the forces in the x direction. We're going to set it equal to 0, bless you. Okay. And let's go ahead and compute all of these forces here. Okay. Okay, so the first force obviously that we have here is from the traction, right? So we said that this T bar is a compressive stress, okay? That means the units for this T here is actually force divided by area, right? Because the units for stress is force over area, right? And so in order to convert that compressive stress into a force, we're going to take that compressive force or compressive stress and multiply it by the cross-sectional area at x is equal to 0. Okay, so this is going to be T bar multiplied by area at x is equal to 0. Okay, good. All right, next contribution that we have is going to be from the body force, just like we had previously. So it's going to be plus b of dx divided by 2 multiplied by dx, right? So once again, we take our body force, we multiply it by the length of our sliver here, just because our body force is a force over length, okay? And then to that, we're going to add n of dx. Right? And that's our internal force that is coming from inside of the structure. Okay. All right, so first thing you notice here, everything is a plus, and so someone has a direction wrong. It's going to be the normal force. Okay. All right, so first thing we're going to do is we are going to take the limit as dx approaches 0. Okay. Right, because essentially we're taking this as the boundary condition, so that's going to be right at the edge there. So if we take the limit as dx goes to 0, that means our b of dx divided by 2 multiplied by dx, that's going to go away because that has a dx next to it, okay? And that means our internal force here is also going to be 0, okay? So what we get is T bar multiplied by A naught is equal to negative internal force at x is equal to 0. Okay. All right, so this is good, but it's not quite there because remember we want to put all of our equations in terms of our deformation or displacement. Okay, so that means for our internal force n here, let's go ahead and plug in our expression, right? So we know that from up here, n of x is equal to a of x, e of x multiplied by du dx. Let's go ahead and plug in for that. Okay. So it's going to be minus a of 0 multiplied by e of 0 times du dx, evaluated at x is equal to 0. Left-hand side of the equation stays the same. So left-hand side, we still have t bar multiplied by a of 0. Okay, so we can see here that we have an a of 0 on both sides. So we're just going to go ahead and cancel those out. Okay, they are the same term. And what we have eventually here is a expression for the boundary condition on the left-hand side. Okay. So we have t bar, or actually let's move the negative to the other side. So we have negative t bar is equal to e of 0 multiplied by du dx at x is equal to 0. So that right there is a mathematical expression that relates the compressive stress boundary condition to our deformation at x is equal to 0. Okay. All right, so in order to form our equations here, we basically need mathematical forms for every single boundary condition that we have. Okay. All right, any questions on how we got this result here? Okay. All right. So in particular, this relationship that we have here, it is a relationship between our T-bar and our deformation, but specifically, it's a relationship between T-bar and the derivative of deformation. Okay. So technically, this is boundary condition relating T-bar to deformation derivative. Okay. And that distinction is actually very important because that kind of describes the type of boundary condition that we have. Okay. So these types of boundary conditions where we have the derivative of our solution related to something else, okay? These are called natural boundary conditions. Okay? Or if you want to go based off the mathematician that discovered this, these are called Neumann boundary conditions. Okay? So Neumann boundary conditions or natural boundary conditions, these are boundary conditions on our solution derivatives. Okay. So that is a good kind of definition to know. Okay. So the words natural and Neumann boundary conditions are the same. The term natural boundary condition is kind of more, I would say, used more in the finite element community. So finite elements like to use the word natural boundary condition. Whereas if you look at from a computational fluid dynamics point of view or numerical methods point of view, typically they use the term Neumann boundary condition. Okay. I just for me personally, I use the term Neumann boundary conditions just because that's just how I was trained. But if you look at textbooks, if you look at papers, you'll probably see the word natural boundary condition if you do any kind of finite element research. Okay, but they're interchangeable. They mean the same. Okay, all right. So that's one boundary condition. The other boundary condition is actually very straightforward because there's no force balance that we need there. Okay. Okay. So on the other side, at x is equal to L, right? So let's look back at our figure here just to kind of see. Okay. Okay. So on the other side of this domain here, we can see that our bar is fixed to the wall. We have our traditional fixed support. Okay. That means that at the wall, right? Because the wall is fixed, that means our deformation must be 0 at that wall. Okay. So on the other side of the wall here, our bar is fixed to a wall. Okay. Right. And so fixed supports we've seen a lot already. This basically means that any deformation there is going to be equal to 0. All right, so these types of boundary conditions are much easier to work with. Okay. So these types of boundary conditions where we are directly specifying the value of the solution. Okay. We're not going through a derivative. We're just saying that the deformation must be 0 there. Okay. So these types of boundary conditions are called essential boundary conditions. Okay. That's kind of the FEA term for it. So in FEA textbooks, papers, you'll see the term essential boundary conditions. But kind of the mathematical term for it is a Dirichlet boundary condition. Okay. So once again, which term you end up using, it's just personal preference, honestly. Most people kind of know that there's both, but for me personally, I learned it first as Dirichlet boundary condition, so you'll probably hear me just naturally refer to that. Okay, but they mean the same thing. Okay. All right, good. So now that we have our boundary conditions in mathematical form, we have our governing differential equation, for our deformation, and we have our domain. We are now ready to state the strong form of this boundary value problem. Okay. Okay. Okay, so the strong form is given by the following, right? So first, you're always going to see the governing differential equation presented first. Okay, so we have d dx of e of x, a of x, du dx, right? So that's our governing differential equation plus b of x is equal to 0. Okay. Right? So every statement of a boundary value problem starts with that. Okay. Next we express the domain, right? So we have a one-dimensional problem here, so we have to basically just describe the upper and lower bounds for the x. Okay. Right? And so in this case, our domain for x is going to be between 0, x is equal to 0, and x is equal to L. Okay. Right, so this right here is our governing equation. Okay. This right here is our domain. Okay. All right. Good. And then we have our boundary conditions. And so we have E du dx evaluated at x is equal to 0 is equal to t bar minus, okay? And then u of L is equal to 0, okay? Okay, so these two right here, these are our boundary conditions. Okay. All right, and so that's everything you need to express the strong form of the problem, okay? Although take note, right? So we express the boundary value problem for this particular case where we have a compressive force on the left and a fixed boundary condition on the right, okay? But in most other situations, your boundary condition is going to be different. So just be aware of that, okay? Okay. So boundary conditions will be different for different cases. Okay. So make sure that you formulate them accordingly, right? So don't just kind of blindly just kind of use this expression here, right? And actually, you'll see that in practice immediately as we're going to do an example right after this. Okay. Okay. All right. Any questions on this before we jump into an example? Okay. All right. So let's do a simple example here, and we're going to solve it kind of from front to back. Okay. Okay. So let's say we have a simple bar exposed to a tensile force. Okay. All right. So we have our structure just like this. So on the left-hand side, let's say we have our pin support. So that's where our fixed support is going to be. On the right-hand side, we have a roller just to make sure that the bar doesn't just fall down. Okay. And then on the right-hand side, we are going to be applying a force, tensile force of 100 pascals. Okay. I guess technically it's a tensile stress. Okay. Right. The properties of our bar here, we have a Young's modulus. It's going to be constant at 100 kPa. Okay. And then our cross-sectional area, we'll say 0.1 meter squared. Okay. Okay. And then let's also say that the length of the bar is 1 meter. Okay, so we have a 1 meter long bar. And so what we want to find out, right, is what we want to do is we want to solve for the deformation of this bar as a function of x. I don't know what happened. There it is. So essentially, we want to form our boundary value problem here. We want to solve for its solution and obtain a function u of x that describes the deformation at all points x within the bar. Okay. All right, we have our governing equation here, or we have our boundary value problem. So before we actually go through and solve our differential equation, let's express our boundary conditions as a function in its mathematical form. Okay. As you can see, hopefully you saw that these boundary conditions are different from the one that we did in our derivation, right? So our fixed support here is on the left, it's not on the right, and we have force boundary condition or Neumann boundary condition on the right instead of the left, okay? And it's tensile. Okay, so first thing that we have here is that at x is equal to 0, okay, right, we have our fixed support, which in this case is a pin. Okay. And so right away we can say that the deformation at x is equal to 0 is going to be 0. Very straightforward. All right, and then at the other side, at x is equal to L, okay, we have a tensile stress. Okay. And so the way that's going to look is that we have it's Young's modulus multiplied by du dx, okay, evaluated at x is equal to L. Okay. This is going to equal to a positive 100. Okay. So notice here we had a positive stress here just because the force is tensile, right? So the fact that our force was negative in our derivation, that led to kind of a minus t bar. But the fact that our force here is tensile, that means we can apply it as a positive stress. Okay. All right, so let's go ahead and solve it. So this is a pretty simple case. Okay. So let's go ahead and write out our governing equation. So let me write out the full equation here, but you're going to see that a lot of it's going to simplify away. So you have d dx of e of x, a of x, du dx plus b of x is equal to 0. Okay. All right. First thing we note here is that there was no mention in the problem of any body force, and so we can say that our b of x here is going to be equal to 0. Okay. Usually if the problem doesn't mention anything about a body force, you can assume it's 0. Usually the problem has to be pretty explicit to mention a body force, okay? And usually it's, for the most part, it's going to be gravity. That's the most common body force that we're going to be looking at. And of course, that only applies to vertical structures, okay? So since this is a horizontal structure, the gravity is not affecting the horizontal deformation in any way. We can say the body force is equal to 0, okay? Okay, the other thing that we know is that E and A, these are both constants, right? These are not varying in x, and so they are just constant values. So we can go ahead and pull them out of the derivative, right? And then what we get is E times A d dx of du dx, right, is equal to 0. All right. And so if E and A are constants, and the right-hand side of this equation is 0, we can go ahead and divide both sides by E and A, so we can cancel those out, right? We apply that derivative in there, and what we get is d squared u dx squared is equal to 0, okay? So very, very simple differential equation in this case. Okay, good. All right, so to solve for this solution, all we have to do is just simply integrate this equation twice, right? So we integrate it once, right? So that's going to cancel out one of the derivatives there. So we integrate once, we get du dx is equal to, integral of 0 is just 0, but since these are indefinite integrals here, we have to add an arbitrary constant. So we have to add a c1, okay? We're going to integrate one more time because we don't want du dx, we want u of x, okay? And so we integrate one more time, we get u of x is equal to c1 times x plus another arbitrary constant because we integrated again, plus c2. So this right here is our general solution. Okay. And then to find the final solution, all we have to do now is apply our boundary conditions. Okay. Okay, so let's go ahead and apply our two boundary conditions. And so first thing we're going to apply is let's apply our Dirichlet boundary condition. Okay. And so the Dirichlet boundary condition for this is u of 0 is equal to 0. Okay. So we plug in x is equal to 0 into our general solution. So we have c1 times 0 plus c2. And so what we get is c2 is equal to 0. Okay. Very simple. The other boundary condition that we have is E times du dx is equal to 100 Pascal. Okay. So we go and plug in the numbers for this. And so we divide both sides by E. And so what we get from that is we have 100 divided by 100 kPa. So that's divided by 100,000. Okay. So that equals to 0.001. Okay. And that's equal to du dx. Okay. Right. So du dx we can obtain from our general solution. So we simply just take the derivative with respect to x. And so du dx is equal to c1. Okay. So that tells us that c1 is equal to 0.01001. So that means our solution here, u of x, is simply equal to 0.001 multiplied by x. All right. So this whole process right here, this is probably how you learned how to solve differential equations in the past, right? So when you solve a differential equation in kind of this traditional way, you obtain your differential equation, you perform some kind of mathematical tricks to get the general solution. Here we could just simply integrate. So just simply integrating gave us our general solution, but sometimes you may have to bring an integrating factor, form the characteristic equation, things like that. Okay. Then you apply the boundary conditions, and then you get your solution at the end. Okay. So that's why I mentioned earlier that the strong form of our boundary value problems is probably what you're accustomed to, probably what you've kind of seen before, right? And strong forms are very useful when you can solve for the solution perfectly like this. Okay, so when we can solve an equation by hand, strong forms are very useful. It kind of lends itself well to that. Okay, but if you're going to be using an approximate method, if you're going to be using like finite elements, strong forms are not that useful, and you'll kind of see why. Probably not today, but probably after the midterm. Okay. All right. Any questions on this? Okay. All right. So for the last 15 minutes of class today, let's introduce the concept of a weak form, and then of course we'll kind of pick this up again after the midterm. Okay. All right, so let's talk about weak form of 1D elasticity. Okay. All right, so this is the part where I think, you guys probably will kind of see this for the first time. Okay, so our starting point for the weak form is actually going to be the strong form, right? So actually the easiest way to get the weak form of a problem is to go from the strong form and then transform it to the weak form, okay? The reason for that is that, a lot of natural derivations, like kind of like the one that we just did, it just naturally lends itself to the strong form of the equation, okay? So to get the weak form, you first have to get the strong form, and then from the strong form, you get the weak form. Okay, so let's start with our differential equation here. So we have d dx of a of x, e of x, du dx plus v of x is equal to 0. Okay. Okay, so that's our strong form of the equation. Okay. One thing I want to kind of point out before we kind of start with the derivation here, okay? It's a little bit hard to see in this form right here, but you can see that the maximum derivative that we have here is second order, right? I think it was a little bit easier to see in the previous problem, but if you apply this derivative and you essentially apply it to this term right here, you get a second order derivative, okay? Now, we're going to see that second order derivatives are actually undesirable in some situations. So kind of our goal, one of the goals of the weak form is to basically weaken the order of the derivative, hence the name weak form, okay? Okay, so how are we going to do that? Because we can't just take a derivative and just take it away, right? That makes no sense, right? But what we can do is we can actually move that derivative to another function, right? So what do I mean by that? So let's take this equation here. Let's take this entire equation and let's multiply it by another function, which we will call w of x, okay? So this w of x is a very kind of special function. But for now, we will just say that this is some kind of arbitrary function of x. Okay. It's not it's applied to the forcing function too. It is applied to the oh no, I'm sorry. This is not a forcing function. We are going to apply it to the body force, but this function here has kind of a special meaning. It's not a forcing function. It's something that's just used in the derivation. Yeah. Okay. So what is this arbitrary function, right? Well, it's a little bit too early. It's a little too soon to kind of reveal that, but we can place some restrictions on the arbitrary function. Okay. Okay, so the requirement that we place on the arbitrary function is that we require w of x to disappear at any location where u has a Dirichlet boundary condition. Okay. Right. So remember, we're only looking at the differential equation here, but this differential equation is part of a boundary value problem. So we already know, or we should know at this point at what locations u of x is going to be equal to a Dirichlet boundary condition. Okay. So the way that we express this is that we basically say that for it's not a for loop. This is just a regular for. So for locations where u at our Dirichlet boundaries, and so that's kind of the generic notation for that. So this gamma u here, this is what we call the Dirichlet boundaries. Right. And so for the location where we are going to directly specify the value of u at the Dirichlet boundary, so u at the Dirichlet boundary is equal to u naught, right? We are going to require w at those same locations, okay, must be 0, okay? That's the only requirement that we're going to put on w at this time, okay? So wherever u has a Dirichlet boundary, now in most cases for elasticity, our Dirichlet boundary conditions are actually 0. But when we get to heat transfer thermal conduction, right, we'll have non-zero Dirichlet boundary conditions, okay? But the same requirement for w is going to be placed there as well, right? So wherever we have a Dirichlet boundary, w at that locations must be 0, okay? Okay. All right, so let's go ahead and distribute this through. So I'm going to take this w of x, and we have essentially two terms here. We have our derivative term, and we have our body force. Okay. So we have w of x d dx of e of x, a of x, du dx, okay, plus w of x, b of x is equal to 0. Where w of x has those properties up above. Okay. Now we're going to do something that you probably did not expect, but we're actually going to take this entire expression and integrate it. Okay. So we're going to take integral of this. Okay. And since we have two separate terms here, we can take the integrals of each of them separately. Okay. So we're going to take integral of the first term with respect to dx, okay, on both cases. Okay. And these are not generic integrals. So these are not the integrals that we did in the previous problem where they had no bounds. Specifically, we're going to integrate this across the entire domain that we're looking at. Okay. And so we're going to integrate from 0 to L. Okay, so these right here are integrals across entire domain. Okay. And that's important. So because we are doing kind of explicit integrals here, we are not going to get any arbitrary constants. Okay. Okay. Good. All right, so now that we have integrals here, and so I know the path is not very clear here. It kind of seems like we're just doing a bunch of random math stuff just for the hell of it, right? But I promise you there is a nice conclusion to this. Okay. Okay, so the second integral, we're actually going to leave that one alone. So there's not much we can do with w of x, b of x. So that depends on the form of b of x, right? But we can actually work on this first integral here. Because remember what we said, right? So kind of before we kind of started deriving the weak form, we said that, we have essentially a second order derivative on that first expression right there, right? So we essentially have d squared u dx squared, right? Now that we've multiplied by w of x, and now that we've integrated it, we now have a mechanism for essentially reducing the order of derivative there, and that's going to be integration by parts. Okay. So you probably did not expect that either. I know first time I learned this, I was like, why are we just doing you're just randomly opening the calculus textbook and just pointing at random stuff, right? But trust me, there's a purpose for this. Okay. Okay, so if you remember integration by parts, we have a u part, okay, and we have a dv part. Okay. So for the u part here, we're going to set it equal to w of x. And for dv, we're going to set it equal to everything else in that expression there. So d dx, e times a du dx. Okay. And then what we do from there is that we take the derivative of our u part, right? So we take the derivative of w of x, we get dw dx. And then for what we selected as dv, we're going to take the antiderivative of that, which is just going to cancel out our derivative there. So this is going to be e times a du dx. Okay. Okay. And then from here, what we then do is that we take our u and v parts, we multiply them together. Okay. Right. So our integration by parts is essentially u times v minus integral of v times du, right? So you may have to go back all the way to Calc 1 or Calc 2 to remember that. Okay. Okay, so let's go ahead and plug those in. And so we do that. We get w of x multiplied by EA times du dx, right? Minus integral, right? And we're still integrating from 0 to L of dw dx multiplied by E times A du dx dx. And by the way, this first term, we've essentially integrated it. And so we're going to evaluate this from 0 to L. All right. So I regret using red for this whole thing. I was just so excited for the integration by parts. Okay. Okay, so what have we obtained here? So, on the one hand, you could say, yeah, we've made a mess, right? So we took a relatively simple differential equation and we made it just twice as long for whatever reason, right? But let's kind of evaluate each of the terms that we have here. Okay, let's look at this one first. Okay, right. So we have essentially the product of w of x times e times a times du dx evaluated from 0 to L, right? So let's go ahead and evaluate that at the integration bounds. Okay. And so we have w of L times e of L times a of L. Remember, because e and a are all functions of x as well, times du dx at L minus, same thing at 0. Okay. So w of 0, e of 0, a of 0, du dx at x is equal to 0. Okay. All right, so what do you notice about these terms here, right? What you should notice from these terms is that we have one term here where everything is evaluated at x is equal to L, and another term here where everything is evaluated at x is equal to 0. Okay, so those two locations are very special, right? Because those locations are the extremities of our domain, right? Because our domain goes from 0 to L, right? In other words, these are locations where the boundary conditions are applied. Okay. And so essentially what we got here is that, we got terms where our boundary conditions are applied, okay? And if you think back, right? If you look back at one of the requirements that we have here is that, our W has a special property where, wherever we evaluate it at the Dirichlet boundaries, then it has to equal to 0, okay? Now, for this particular case, we haven't specified where the Dirichlet boundary condition is, but for every boundary value problem, you have to have at least one Dirichlet boundary condition. Okay, you can't have all Neumann boundary conditions. That means one of these will equal to 0, okay? Because either W of L or W of 0 has to equal 0. Okay. Okay. Whereas the other term here will be a either, well, they could both equal 0 if we have a Dirichlet boundary condition on both, but whichever one is not equal to 0, that's where our Neumann boundary condition is. Okay, so essentially, we've taken our boundary conditions and we kind of baked it right into the problem. Okay, and the last thing I'll say, just so I know we're over time, is that if you look at the other term here, the other integral here, right? We've accomplished our other goal for this weak form is that, we've taken our derivative from one term and we've kind of shifted it over to our W term, right? And so if we look at all the derivatives here, the highest order derivative that we have is 1. Okay. Okay. And that right there is actually very significant. So then, what we'll see after the midterm on Thursday is that this allows us to do what's called an approximate solution. And we can use, very kind of low value functions like a linear function to approximate our solution. And that itself is very valuable. Okay. All right. So thank you guys for coming today. I apologize for going over time a little bit. If you have any questions leading up to the midterm, I'm available on email. But if not, I'll see you guys all on Tuesday for the email. Okay. Question. So on the midterm 1 review, there is a MATLAB section call out. Is that just from an old version? Or is that something that will be covered? So midterm 1, so I used to do a MATLAB conceptual question on the midterm, but I will say that on this midterm, there's no MATLAB question. I figure there's more important things for us to cover. So yeah, so for this midterm, I thought about it, but you don't have to worry about it for the midterm. Yeah. Okay. All right, thank you guys. I'll see you guys next week. Nope. As long as you don't have the exam answers, but you would probably have to hack my computer or break into my office. It's not an invitation, by the way. Please don't break into my office. But now that I've said that, I'm gonna take them home. So please don't break into my home. I just bought it.
Congrats.
Oh, thank you.
Let's just add it. So okay, I know trust.
Yeah.
Scripts. Yeah, so no frames.
And also for like trust, you like how you go from 1 to 2.
Yeah.
One of those weird steps in the middle. The stress. Worrying about that.
No. Just because we can't compute solutions on the exam because we don't have that. So there's no stress and no reaction.
Yeah.
Okay.
Yeah.
I'm not gonna lie to you, I'm trying to catch up, right? So I'm going through like the lectures online,
Mhm.
and like I'm just today I'm